Hola, buenos días a todas y a todos y muchas gracias por estar aquí. El día de hoy tenemos el gusto de tener con nosotros el maestro Ludovic Chender, que nos va a presentar un seminario con el título Reconstructing Lava Flow Emplacement at the Lemptegy Volcano, a monogenetic cone in the UNESCO-listed Chaine de Puys, France. Antes de empezar, voy a leer una pequeña semblanza de Ludovic. Ludovic es estudiante de doctorado en la Universidad de Clermont, Auvergne, donde anteriormente realizó tanto la licenciatura en geología como la maestría con un enfoque en magma y volcanes. Durante sus estudios realizó varias prácticas en el laboratorio de magma y volcanes. En estas prácticas estudió la geomorfología del lago de Cuenca en provincias volcánicas, así como investigó procesos de desplazamiento, de emplazamiento y enfriamiento del flujo de lava del volcán Lemptegy, también localizado en la Chaine de Puys. Actualmente su trabajo se enfoca en la deformación y emplazamiento de flujos de lava, así como los depósitos de ceniza y geopatrimonio. Ludovic, many thanks to be here today, and please go ahead with your presentation.
Okay. So, hello everyone. First of all, I would like to start this presentation by thanking all the people who organized this presentation for giving me the opportunity to present a small part of my research. So thank you very much. Muchas gracias. So today I will discuss about how vesicle deformations and field observations can retrace the emplacement story of a lava flow. And for that, I studied a very well exposed lava flow from the Lemptegy volcano in France. So, let's move from the UNAM and let's cross the Atlantic Ocean to reach France, and more specifically, the center of France, where over 80 volcanoes are aligned from the north to the south, and have experienced different types of eruptions, leading to different types of volcanoes, such as scoria cones, domes, spines, cinder cones, etc. And this monogenetic volcano have erupted on a period over ranging from 95 to 8.6 thousand years ago. And this monogenetic field is called the Chaine de Puys and is located on an high plateau, which is separated from the Limagne Basin, where the city of Clermont is situated, by the Limagne Faults. And these Limagne Faults and these monogenetic fields have been listed as the UNESCO World Heritage Sites in 2018. So now let's enter into this Chaine de Puys to reach the Lemptegy volcano, and is located on the center of the Chaine de Puys. And this volcano before 1945 looked more like this, because just after the World War II, we started to dig into this volcano because France needs a lot of materials to reconstruct the buildings who have been destroyed during this war. So now the Lemptegy volcano looks more like this, and since 2006, we have totally stopped to quarry into this volcano. And now the owners have made the transition between quarry to a very well-known geotourism and science place, where over 200,000 visitors come to this volcano each year, especially during the summer. And finally, the owners have replaced the quarry machinery, to electrical trains. Yeah, we have one diesel train, but to transport over 80 visitors each hour into this volcano. Okay, now let's remove the snow to have a better view on this volcano. And if you ever have the chance to visit this volcano, I don't say that because I'm a guide during the summer in this volcano and I'm working on my PhD on this volcano, but you will have the chance to see several structures that you cannot see on still active volcanoes, such as cryptodomes with the feeder dike that feed the cryptodome, spiral cones, or dikes with bend. And more especially, the most important things that has been discovered on this volcano is during the excavation. In reality, some studies have shown that there is not only one volcano, but two volcanoes distinguished by different chemical compositions. So there are Lemptegy 2 and Lemptegy 1 volcanoes. So the Lemptegy 2 volcanoes has been described as a scoria cone, a trachyandesitic scoria cones that erupted 29,000 years ago. And there is the Lemptegy 1, who erupted 30,000 years ago and consists of a trachybasaltic cinder cones organized around 4 dikes, with the late emplacement of the dike 4 that's produced a very small lava flow directed to the northeast. And this lava flow was first described by Delcan et al. In 2014 as a small pyoyoy flow directed to the northeast, and with that's emplaced on the tephras of the Puy des Gouttes. The Puy des Gouttes, it's a volcano which is located just few thousand of meters to the north, just nearby the Lemptegy volcano. And when we have a better view on this lava flow, we can see several structure and vesicle shapes that are not very common in pyoyoy flows. So we can ask, how can we retrace the emplacement story of this lava flow? But before answering this question, let's back to 1953, where McDonald's described 2 main types of lava flow. In reality, 3 with the block lava flows, but two main lava flows. So there are pyoyoy and AA lava flow distinguished by different surface texture, different flow styles, and different vesicles. So the pyoyoy flows can be more compared to this Yunnan duck, with a very smooth, very glassy, and very coherent surface. And where the AA lava flow can be more compared to this dragon, which is more rough, more clinkery, more blocky surface texture. And these 2 types of lava flow have different flow styles, where the pyoyoy will advance as a thin, low viscosity, highly vesicular flow. The AA lava flow can advance as a thick, very viscous, less vesicular flow, advancing faster, creating more shearing, leading to the formation of the clinkers at the surface of these lava types. And some studies have tried to explain the difference between these 2 surface textures. How can we form these different types of structures? So first, several models, such as FlowGo in 2001 by Harris et al., have shown that they explain the different surface texture by mainly control of the rheological condition parameters during the emplacement of the lava flow, such as the viscosity, the surface cooling, the strain rate, etc., but also on the topography. And on 1980, Peterson and Tiding have shown that it exists a transition between pyoyoy and AA lava flow by or increasing the viscosity by cooling, or by increasing the strain rate by a variation, a change in slope during the emplacement. But anyways, as the lava emerges from the vents, she immediately starts to cool, and several thermal layers will start to form into the lava. So there are the viscoelastic and the brittle layer that will form both at the surface and at the bottom of the lava. So they form at different isotherms. So the brittle layer will form at 800 degrees Celsius, where the viscoelastic layer will form at 1070 degrees Celsius. And depending on the strain rate, on the shearing, the bubbles into the bottom viscoelastic layer will deform in the sense of shearing. And as the brittle layer will grow, she will capture the different shapes of the vesicles during the emplacements. And as this brittle layer grows, she can retain the steel fluid core in movements just over there. And as more lava is supplied, the viscoelastic layer, the upper viscoelastic layer, will accommodate this pressure by growing, by expanding, but the brittle layer above cannot accommodate this pressure and will start to fractures, leading to the formation of some inflation structure that are well visible on the field. And to reconstruct the emplacement story of our lava flow, we have based our study on the field work. So we made first some photographs. So we divided our outcrop into 9 sections that we photographed from the bottom to the top to have very detailed images of the vesicle shapes. After that, we sampled each section at the upper crust to have more primitive information about porosity and crystallinity of the lava. And finally, we made some measurement of the geometry of the lava, such as the slope, the thickness, etc. So back to the lab, we processed our photographs. So we first binarized our images thanks to the Adobe Photoshop software. So we obtained black and white images where the black consists of the vesicles and the white the rest of the lava. And after we have analyzed these black and white images on the ImageG software to measure the different vesicle shapes parameters such as circularity, elongation, etc. After that, we use the samples in different ways. So we first measured the vesicularity and the density of the samples thanks to the helium pycnometer at the laboratory magma and volcanoes. And we made some thin section of the samples to measure the crystallinity of each section. And finally, we crashed one sample into a powder to analyze this powder with a mass spectrometer to measure the bulk chemistry of the lava. After that, thanks to from our lab's measurements, we were able to estimate, to calculate a viscosity and a cooling model. So we first calculate the apparent viscosity with the equation of the Giordano et al., which simply depends on three parameters and the temperature. So there's the parameters A, B, and C are automatically calculated from the bulk chemistry of the lava we measured just before. And after that, we have corrected this viscosity considering the vesicularity, the porosity, and the crystals, thanks to the equation of Fantien, just over there. After that, we were able to calculate time of total solidification using the relative time of solidification of basaltic body described in Turcotte and Schubert in 2002. That depends first on the thermal conductivity that is calculated thanks to our porosity measurement, and after we were able to calculate the thermal diffusivity by this equation after we put this thermal diffusivity into this equation, and we have the time. Yeah, that's look easy, but not easy at all. And finally, we were able to calculate the velocity profile of each section using the equation of Sigoldi in detail that depend on three main parameters. So the density, the viscosity, and the slope of the lava. And thanks from this velocity profile, we derivate the strain rate, which is simply the velocity gradient per unit of thickness. And thanks to the strain rate and other measurements, we calculated the capillary number. The capillary number is to understand which force it dominates within the flow, or it's the viscous forces or the tension force around the bubbles. And if we have a capillary number greater than 1, it means that the viscous forces will dominate and the bubbles will elongate in the sense of tearing, so in the sense of flowing, finally. So, from our field observations, we observed several things on the field. So first, this lava consists of a 0.6 meter thick sheet flow emplaced on the tephra of the Puy des Gouttes. And this lava flow was emplaced on a very variable slope ranging from 80 over there to 48 over there, sorry. And that's the northeast slope, okay? So this lava flow is sandwiched between the tephras of the Puy des Gouttes, but what is striking over there is that the tephras just beneath the lava flow are reddish and highly fracturated over there. And we can also divide this lava flow into three main parts, distinguished by different surface texture, ranging on the left with AA mature with clinkers up to 20 centimeters, so that's huge. The center part is characterized by AA mature surface texture with clinkers up to 5 to 10 centimeters, so less than the other one. And finally, the rest of the lava is characterized by spiny poyoyoid texture. It's very small spines of lava that are related to the lava. But we also observed some very small scale inflation structure just over there, mainly on the center of the lava flow. And when we have a look on the vesicle deformations, we can observe three main layers into the lava flow with different direction of shearing. The first one is the 10 first centimeter thick layer from the base. It's characterized by very rounded vesicles in the parallel plane, so the northwest southeast plane. But when we have a look on this close-up, it's the perpendicular plane. We can also see that these bubbles are very elongated in the perpendicular plane. Above that, there is a layer that's ranging from 0.3 to 1 meters of highly deformated vesicles to the southeast, just over there, in red and orange. But it's totally the contrary than the first layer. These bubbles are rounded in the other plane, so in the northeast plane, but elongated in the other plane. And finally, the last layer is characterized by rounded vesicles in all directions, and that's totally consistent with the upper layer of lava flows where strain rate occurs. Okay, so from our lab measurement, we were able to observe that this lava consists of a trachy basalt. So we can that allow us to estimate a temperature of eruption of about 1,150. We obtained bulk density ranging from 1,480 to 2,000 kilogram cubic meter, and porosity ranging from 23 to 49, and crystallinity from 8 to 25%. All of these results allowed us to calculate a three-phase viscosity that ranging from 80 to 1080 Pascal per second at the temperature of the eruptions. And to that and the field measurement, we were able to calculate the velocity of each profile that ranging from 2 to 8 meters per second. And we derivate the strain rate thanks to this velocity to have a strain rate very huge of 10 to 43 per second. But that's consistent because we have very steep slope upon the lava. And finally, we estimate an effusion rate thanks to the flow geometry and with a mean velocity that we chose of 4 meters per second. That's allowed us to calculate an effusion rate of about 75 plus or minus 25 cubic meter per second. And that's consistent with some lava flows that have been estimated by Harris et al. For Etna flows or some Hawaiian flows also. And finally, we calculated the capillary number thanks to all these informations. And we can see that upon the lava, the lower capillary number are found in the northern parts, and the highest values are found in the southern parts. But that's very consistent with the vesicle shapes elongations that are very, very elongated in the southern parts with higher value of capillary number and low deformation on the northern part. That's consistent with our values results. And finally, thanks to our porosity measurement, we were able to calculate the thermal conductivity and thus the thermal diffusivity of our lava. That allowed us to estimate total solidification for each section. And that's varying a lot because it's depend a lot on the thickness of the lava. And as we've seen, the lava is not constant at all. So we estimate total cooling time from the northern part of around 7 days. And for the thickness part, it can reach 33 days, around 33 days. So here it's a briefly summary of our results. We have divided our lava flow into 3 main sections. The northern part is characterized by AA mature clinkers up to 20 centimeters. The thickness is not varying. The tephra just beneath the lava flow are highly fracturated. and velocity calculated are relatively slow for a near vent eruption of about 2 to 4 meters per second. And finally, we derivate the strain rate for 10 to 25 per second. And it's over there that the cooling time is the lowest, with 7 days, approximately 7 days. At the center, we observe the surface texture of AA mature with clinkers reaching 5 to 10 centimeters. We can also see some figure of inflations of about 0.9 meters thick. And we calculate velocity higher than the left part, so a cooling time of around 12 days. And finally, the last part is the southern part. That's surface texture is characterized by a little spine of lava. It's called spiny pyoyoi, and that's characteristic of transitional lava flows between pyoyoi and AA. And this part is very thick if we compare to the other parts. It's ranging from 8.9 to 8.2 meters thick. And we have calculated velocity greater than, faster than the first part, but very coherent with the center parts. And with cooling time over 14 to 36 days. So that's much than the other parts. But the common points of these different parts is there is two preferred direction of chairing. The first 10 centimeters of bubbles are chaired in the northeast direction, so the perpendicular direction. And above that, we have another layer that shows some bubbles elongation to the northeast, to southwest, sorry. So this direction, parallel to the lava. But that's not very coherent. What we found that's not coherent. So we found lowest strain rate over there with figure of clinkers. Normally, when you have a lot of strain rate, you create a lot of clinkers. Here you are over 40 per second. Here over 10 per second. But we can see the surface texture of spiny pyoyoi in this part, but not on this part. So that's not coherent. And we cannot explain this different observation by only flowing from this point to this point, because we cannot, Peterson and Tiling in 1980 have shown that it's not possible to have an AA to pyoyoi transition, only a pyoyoi to AA transition. At this small scale, it's impossible. So how can we interpret this observation? So, wait. We interpret these results as a first emplacement of a jet flow over about 0.6 meter thick to the northeast. That's stretching the vesicles of the first layer to the northeast. And this lava flow in place on a very variable paleoslope, creating more strain rate in the northern parts, leading to the formation of the clinkers in this part, and a gentlest slope in this part, creating spiny pyoyoi texture. After that, that's very common at Lemptegy to have some cryptodomes. So the formation of something that uplifts a cryptodome or seal. We have a lot of bulge structure just nearby the lava. So an uplift of the northern part of the lava. So yeah, just before the uplift, the brittle layer have captures in the 10 first centimeters of the flow, the first direction of emplacement to the northeast. After the uplift, we have a change in direction of flowing of the lava, flowing this time to the southeast, stretching the vesicles to this direction. And after that, the brittle layer will grow and capture the different vesicle shapes. And we have a total solidification of about 33 days around with our calculations. And this model is very coherent with our results of surface texture, flow geometry, and direction of vesicle deformations. So in conclusion, we use some field observations such as the flow geometry of slope, thickness, etc., and vesicle deformation, and our laboratory analysis with crystallinity, vesicularity, and chemical to retrace the rheological condition from through viscosity and cooling model. And we retrace the emplacement story through the vesicle deformation of the lava, the Lemptegy one pioneer lava flow. I would like to sincerely thank the Lemptegy team. So that's the owners. It's a family company. So there is Luca, Philippe, and Timothée, who accompanied me for a lot of things during this study. So Timothée provided me a lot of materials, and Luca and Philippe provide me the free access to the Lemptegy volcano. And thanks to Andraris, who supervised me during this study. And I would like to thank the ECOS project. It's thanks to them that I'm here in front of you today. So thank you very much for the ECOS project. And finally, I'm not working only on lava flows. I'm also working on ash deposits and on heritage. So if you are around in France one day, if you ever have the chance to come to Auvergne, very nice region of France. Yes, we have good cheese, good food, good dishes. But if you are around, you can contact me at this email, and I will make you a private tour of the Lemptegy volcano if you want. So thank you very much. And if you have questions, I'm there. Thank you.
Thanks, Ludovic, for your presentation. Any questions? ¿O algunas preguntas para Ludovic? Por las personas que están aquí o por quien está en línea.
Okay, thank you, Ludovic. It was very interesting. My question is, I saw that you considered your strain rate only with respect to height. Is that correct?
Sorry, can you?
Yeah. Your strain rate, the gradient in your strain rate is only with respect to height. So only with respect to the sea direction, right?
If we compare to other Hawaiian flows, it's very high, but we are near the vent with very high slopes, so that's consistent.
But do you think that maybe these results of the change in the direction of the vesicles that you were having trouble interpreting could be resolved adding the other directions to this gradient?
So we have observed this elongation in the two directions. So it's very consistent.
Well, okay, thank you.
Thank you, Ludo. I have two questions. The first one is regarding your methodology. And I had a question when you took pictures of the vesicles and you convert them into binary images. What is the margin of error with doing this? For example, if there is a very cloudy day, for example, would you have more, shadowy parts in your picture?
Yeah, we corrected all these things. So we have to, the good weather, it's our friends during this types of methodology. So after when we binarize these images on Adobe Photoshop, we manually select also the vesicles, and we can just remove the artifacts like shadows or. So it's very depending on the human. So if you do that at night at 2 a.m., it's complicated. But I also show the images. We compare the images, the original images with the binarized images. So that's fit very nice. So
Oh, okay. So it's not automatic yet.
No, you at first, it's automatic. So you can do it automatically, but after you have to correct if you have some artifacts. But at first it's automatic.
Okay, thanks. And my other question is, how are the lavas in the Lemptegy volcano different from the ones here in CU or in Mexico City, for example?
Sorry?
How are they different?
From the Mexico's lava flows?
Yeah.
So the composition first?
Yeah, the composition or...
the composition. So there are... Here in Lemptegy, we have only near the vent lava flow, so it's very thin flows. maybe imagine if our lava flow that we studied here, if we see her in one kilometers far, we can have some pyoyo flows that can reach some 2-3 meter thick. So we can compare these types of lava flow near the vent and the one we have here in the campus, for example, because in the campus here in the UNAM, it's far from the vent. So they are more inflated, so more thick. And we can compare and make some comparison between near the vent and far from the vent. But we have to consider the slope too. The slope will influence a lot of on the physical deformations, and also on the composition that's influenced a lot of on the viscosity and thus the velocity, etc. So yeah.
Okay, thank you.
Welcome.
Thanks again for your talk.
¿Algunas otra pregunta a las personas presentes en el auditorio? Tenemos...
Well, thank you, Ludo. I hope it's not your only time in Mexico. I hope you come back. And my question about the textures of you mentioned in your picture, you show the textures at the base of the flow, if I don't. But then you interpret it as a surface textures. So it's, I'm a bit confused here, and whether the same, can you also see the surface? And what if you find the same structure at the top, at the base of the floor?
Yeah, we don't have access to the top because of the quarry. I think the top is a little bit has been a little bit destroyed, but we can observe the basalt surface texture, and it's coherent with the surface texture because when the lava advances, the surface texture on the top can fall and arrive to the bottom of the lava. So the texture we saw, like the clinkers, for example, the clinkers forms at the top of the lava and will running up and fall in front of the flow and will be at the base after that. So that's a nice proof of the strain rate over there. So yeah, it's coherent because we talk about surface texture with pyoyo, spiny, AA, but the surface texture will fall in front of the flow and will be at the bottom after that.
Yes, because sometimes it's a bit different in overall when you have these transitional kind of textures, but it's what you have, so that's okay. And yes, I have for your temperature. I didn't understand how you.
Yeah, it's for the eruption temperature. Yeah, it's an estimation from that's largely accepted by the literature that for trachybasalts it's around this temperature, this type of temperature. So yeah, of course we can do some barometry to be more precise, but here for the model it's very simply model to try to reconstruct the emplacement. So that's coherent.
Okay, thank you.
Tenemos preguntas también de algunas personas en línea. Adelante, Alessio.
Hi, Ludo. Thank you for this nice talk. I really enjoyed it. My question is about if your methodology that you applied in the case of Lemptegy volcano can be applied in other volcanic contexts similar, and as well if you think about to apply this methodology in other volcanic contexts.
Have you understand something? Yeah,
more
because
or less.
the noise. Okay. Yeah, can you repeat slower?
Yeah.
Because the sound is on the room.
It's not very good, actually. Okay. Can you hear better now?
Yeah.
Yeah. More or less. My question was, well, first of all, that was a really nice talk. And my question is if you can apply your methodology that you are applying to the volcano de Lemptegy in other volcanic contexts similar to him, and if you are looking to apply in other volcanic contexts.
In Mexico. So, okay, now I understand. Yeah, of course we can apply our methodology to other lava flow in the world. but we have to consider the change in composition that change the viscosity. We have to, here in Lemptegy, we have the chance to have a very nice exposed lava flow. We can calculate all the geometrical flow of the lava. So if you have the access to this geometry, if you can sample, if you can have all these different measurements, yes, you can apply this this methodology. But here it's for basaltics, trachybasaltics methodology, of course. But yeah, we can apply this to the Chitle lava flow. Yeah.
Yes, thank you. And the other question maybe, are you, during this study, for example, during as well your master degree, have you find any kind of limitation concerning the methodology that you are applying?
I don't understand.
In this case, I don't understand anything.
Well.
Maybe can you write it somewhere?
Can you write your
question?
question?
If we have, if you can write it maybe, or yeah, write it on the chat and I will see it. Thank you.
Well, just a moment then.
Mientras Alessio escribe, ¿alguien más tiene alguna pregunta de las personas presentes?
Hi, I can see you're using geochemistry.
Yeah.
That's your methodology, but have you ever thought about another, I don't know, like physics, geophysics, like AMS or something like that, to see if your data match with AMS data?
Yeah, it can be good to do that. I don't have to think about it for now, but yeah, I was more interesting about a general geochemical composition, not about very precise. But yeah, it can be very nice to compare this result with, for example, yeah.
Okay, and I don't know, maybe there with that methodology you could see subtle characteristics about the flow, right? And it could be easier to do a correlation and the interpretation of the data.
To be honest, I'm not a geochemist, so I don't really know about it. So to be honest, I prefer to not answer this question. But it's a way to, maybe in lava flows we can yeah, with this type of methodology to maybe track a change in geochemistry upon the thickness. It can be very nice to retrace the viscosity evolution, for example, within the thickness of the flow. So yeah, that's a very nice explanation. Yeah, I think.
Thank you.
Thank you very much.
Thank you.
Okay, Alessio, right to your other question. Did you find any limitation in your methodology as well during your master degree?
Sorry? A limitation of
Do you find any limitation in your methodology during your master
limitation,
degree?
Sorry. Yeah. Some limitation during my, yeah, because this study is from my master degrees. Some limitation. No, in reality, no, because I have full access to the lava. I can sample as I want. I can make the measurements. It's a very well exposed, so no limitation, but maybe, that's a good question, Alicia. No, I don't think so, no.
Okay, thanks for your answer.
Thanks, Ludo. About your heritage, how do you, I know, and now you told us that you were a guide in Lemptegy volcano. How do you explain this to tourists? I mean, the lava system.
The lava? So I'm a guide, so I'm driving a train, and with the train, we have the chance to stop in front of this lava flow. And to be honest, it's a little bit complicated with the time we have to do the visits to explain this lava flow. So we just pass in front of this lava flow. We said that's a lava flow that's come from the Lemptegy one on the left. that's some place in this direction, and that's all. Yeah, it's very hard to explain the something like this to tourism. Even during the summer. During the summer, it's a lot of family. There is a lot of children. That makes a lot of noise in the train. So yeah, we just said that this lava flow. Oh yeah, during the tour, I explaining that I made some study, but I don't. If people are very interested, 10 minutes after this stop, we stop at a point where we all go out from the train and they can ask me questions. And if they are very interested, they'll come to me and ask me the question about the lava flow, and I can explain after that.
Thank you.
¿Otras preguntas? Another questions? No? Okay. Thanks you, Ludovic, for your presentation.
Sure.
And gracias a todas y a todos por estar aquí, por las personas presentes en el auditorio y también por quien siguió este seminario conectados en Zoom, en YouTube o en Facebook. Muchísimas gracias.